All right, so today we're going to be talking about deeper NLP. So just to reiterate, this stuff is the stuff on word vectors, which I will get into. Word vectors is actually, well, word vectors, word embeddings. Word embeddings are kind of word vector. Word embeddings are in your appendix. And I'm going to talk very quickly about topic modeling, which is sort of like a soft clustering method um, for text data, and that isn't in our curriculum, but I do think it is interesting. And if you want to try that out, you don't have to for phase 4. You don't have to do any of these if you want to do a phase 4 NLP project, but if you would like to, feel free as well. I will say, because this stuff isn't in the main curriculum, I will be using material from other cohorts. So just so you know, here I have linked this repo. This is linked to the exact slideshow I'm going to go through right now. But if you're just curious as to see like what, and this is actually a campus cohort. So if you just want to see some of their material, it is on here. It's going to be quite similar in terms of like the topics are the same, but some of the notebooks might be different. So if you just want to like maybe source other material for something that you're not, that you just want more clarification on, for example, feel free to look into here. They are organized by mods as well. So yeah, just FYI, this was like the last campus cohort that I taught. So a lot of it will be similar to the stuff that I have, but yeah, some of the things are different. All right, so just a quick rundown of what we're going to talk about today. We're going to talk about word vectors, which is basically another way to represent words in like a data frame. So we'll be talking about it in two libraries, one called GenSim and one called Spacey. And then we'll be talking about topic modeling, which is that soft clustering thing I was talking about. So here we're already going to get into code. So before the code, I'm going to run through some like overall, what are word embeddings? And I'll use these slides to talk about that. So the whole thing of word embeddings and why we even have word embeddings to begin with is because we're trying to teach the computer or the machine meaning of words. So therefore, existential question, what is meaning? So meaning has these like dictionary definitions, right? So the idea that is represented by a piece of text, whatever the idea a person wants to convey by using words, or even more abstract, idea that is expressed in a work of writing or art. So meaning has many different levels. And I think that's why it's so hard to teach a machine context and like, yeah, main ideas of what you're trying to get across. So really quickly, some of the more direct ways computers can try and interpret language. These are two methods that we should be kind of aware of. Firstly, synonyms. And by synonyms, I mean like literally like hard coding out your synonyms, right? Some downsides to synonyms are that, like, let's say you have this dictionary saying that, all right, every word that is synonymous to good, we're going to just map that to the word good. Every word synonymous with bad, we're going to map that way. And well, some downsides is with different contexts, like just imagine sarcasm. Synonyms are not going to work out. So only true in certain sentence contexts. Synonyms are also subjective. Again, it's very, very dependent on the situation you're using certain words. And also imagine with all this new like language that's being created as the years go on, very, very hard to update new words and slang, as well as like, yeah, a manual upkeep of like some thesaurus. Even if someone were to have, a Python library that has, everything that is a synonym with it, everything that is a synonym with everything else, that would be a lot of work to upkeep. Another way a computer interprets language, which we talked about yesterday, is through like a count vectorizer or TF-IDF. Now, these two methods, as we talked about yesterday, are bag of words methods, meaning that, what this captures is just, the amount of each word in each document. But there's no notion of like similarity or meaning of individual words, right? So let's say you have a piece of text that is talking about cars. You're going to have all this like car lingo in the text, but your model is going to read each car related word as a completely different word. It cannot draw similarities between, I don't know, wheels and tires, or like, I don't know, what are other car terms? Like, I don't know, the amount of miles per gallon. Yeah, things like that. It's unable to draw similarities between those words. And you can imagine, if you're able to find out, if you're able to somewhat embed that, a tire is kind of synonymous to a wheel, that might be more helpful for your model. And yeah, count vectorizers and TF-IDFs, they really only give context of importance in a corpus. So for example, if you have like a group of texts talking about hotels, yes, through your TF-IDF, you might find out that, all right, similar bag of words, Plaza Hotel and Waldorf Astoria, which are two big hotels, should have a high similarity, but this is only determined by the other words used in, the bag of words for those texts. So yeah, any questions about this before we get into what we're actually going to talk about?
When we are talking,
go ahead, Ollie.
I'm sorry. When we are talking about the synonyms, is it somehow related to semantics or no, just the similarities about these words?
I would say more about the similarities about the words. Yeah.
Oh, okay, thanks.
Mm-hmm.
So,
Sarah?
do you have to like physically make your own thesaurus for this, or you would like?
Oh, like if you want to make a synonym?
Thesaurus? Yeah.
Yeah, I will say that you're not going to do this. This is just like theoretically how a computer would, learn meaning.
Oh, okay, got it.
Mm-hmm. Yeah. Anything else? All right. So the way that we get around that, and let me zoom in a little so this fills up the screen. A way that we get around that is distributional semantics. So rather than, mapping the meaning of words, we can sort of infer the meaning of words by the words that frequently appear around it. So yeah, when a word appears in a document, its context is the set of words that appear nearby, usually within a fixed size window. So for example, if I want to maybe train a model to learn the meaning of banking, I will basically have a window, and this is basically a window of 5. So basically it's going to look at the 5 words before, 5 words after. And basically as you're feeding in many, many examples of sentences with the word banking, the machine will sort of recognize, what are some common words that come around the word banking? Or what are some of the common words that come around banking? And then basically what will happen, and we'll see later, you can sort of represent the word banking as a series of numbers that are probably a combination of all of these other words that are around them. We'll get into more of like these details, but questions about the idea of distributional semantics? All right. Well, this is probably one of I think a really, really big advancement in the world of NLP, because before this, it was hard to determine as I was talking about before, it was hard to decide how we teach a machine context. And literally, a context of a word is defined by the words that you use with that word. So that's where that idea comes from. So word2vec, which I guess stands for turning a word into a vector. How it really works, it does have some neural network components. So that I think will make more sense when we talk about neural networks next week. But basically, oh, yes.
In the last slide. Yeah. How is it helping to learn a machine to know, for example, what banking means based on its previous word?
So for example, it's going to remember that, okay, if I have the word banking, these are words that typically come around banking, right? Like debt, 2009, regulation, certain countries like Europe, and Europe's not a country, and India, and like systems. Basically with a lot of examples of banking, imagine you're not just going to do this with banking, you're going to do this with every other word. So let's say one thing that comes with banking, let's just say debt, right? So imagine if we're taking all of the windows of words around banking and all of the windows of words around debt, you imagine that they become, just by the nature of training these two words on the information around it, you're going to end up with somewhat similar representation. If that makes sense. Like you can imagine the words that surround the word banking are going to be more similar to the words surrounding debt compared to the words surrounding trees, for example. And so it's basically, yeah, it's just how words are distributed when you're talking about specific things. Was that helpful?
Yeah, thank you.
You're welcome. Oh, anything else before? Mm-hmm.
I was just saying that vector space, you'd probably see like similar vectors for money or loans or finance, correct?
Yeah, absolutely. So words that are often used together will be more similar. And I actually do have a couple diagrams that I'm going to show that how we can show similarity between vectors. And we have actual like concrete examples where we can run similarity of vectors. And after, I'll go through those after this. But yeah. All right. So very quickly, word2vec and what word2vec is basically turning words into vectors by way of, not by way of, but with including, you know, all of this context. So what it's doing is actually using one layer of a neural network to create these embeddings. So each word can be represented by a set number of numbers. So we'll actually take a look at some examples later. Some pretty common like vector lengths is like 100. I know 96 as well, because I think 96 is something to do with like the bytes, byte size. And then like 300 is pretty common. So basically, there are libraries that have already been trained on very, very large sets of text. Like Wikipedia is one example. The one I'm going to use is actually trained on Twitter, a bunch of tweets. And yeah, basically through that, they have found representations of individual words that are like for each word, and we'll take a look at that later as well. For each word, it's represented by like 96 numbers or 300 numbers. So what those numbers are, they are abstract. Like you cannot say like, all right, this first number in the vector refers to like the fact that coffee has caffeine. That is not the case. It is it's an abstract representation, kind of similar to the way of like, it's a similar concept as like PCA, where it's, you know, it doesn't really mean anything. Each principal component doesn't mean anything, but it has the information embedded within the numbers. So yeah, it captures the meaning of words in a corpus using a predefined window of words. So in this case, the window is, I forget if they say 5 or 10, but same meaning. There's two kind of different implantations of like how you create these vectors. I have a quick diagram to show how that works in a little bit. And also what's great is there are readily available pre-trained embeddings, and I'll talk about what pre-trained means later as well, on different corpora, such as Wikipedia. Like I mentioned, some of these word embeddings have been trained on all of Wikipedia. Google News is another one. Twitter is a common one, and I actually have a link to a bunch of common ones, so we'll take a look at some of those sources later too. So with these two different kinds of ways you create vectors, again, this is kind of neural network stuff. So hopefully with this information, plus the information we get later in neural networks, it'll kind of come together. So there's two main models used to create word vectors. First, you have your continuous bag of words, which is this one here, and then skipgram. So continuous bag of words, the main difference between this and our bag of words that we did yesterday is that it's continuous. It recognizes the successive nature of sentences. So for example, if you want to train a model to know what spiky means, you would input the words around it and then basically have the model learn through the input words what spiky is, what spiky could mean. And then skipgram is kind of the opposite. It's kind of hard to explain how that is, but through different kinds of inputs, you can basically train your outputs to know, all right, what are some words that often surround the word spiky? This is pretty abstract and yeah, pretty advanced as well. But hopefully after we talk about neural networks, I'll see if I can like weave this into when we talk about this kind of neural network, hopefully. But these are just like two of the if you hear any of these words, just know these are in creating the word vectors. Questions before we move on?
These two projection in these two models are the same or they are different?
They are different. They are different. So this projection layer is something that has been trained, and basically it's how it maps inputs to output. So yeah, they're going to be different.
Okay, thank you.
Yeah, how do we define corpus in this situation?
Oh yeah, corpus is, I guess in this scenario, the corpus would be like a document.
Okay, that's what I was thinking.
Or more specifically, if they're saying like captures the meaning of a word in a corpus, it's you could define it as like every time, let's say the word banking occurs, the window could be the corpus. I will say the definitions are a little wishy-washy here, but yeah, usually corpus just means like an instance of text.
So it can be like every occurrence of the word more than every document?
Yeah, because especially when you're trying to train word vectors, you do want to give it. So let's say the word banking appears like 5 times in a certain document. In training word vectors, you want to consider each occurrence of banking as a training example. So therefore, each occurrence of a word will become the document.
Okay, great.
Okay, sounds good. Anything else? All right, so just as I mentioned, I have some graphs to show like what this means. So these are superlatives, you know, like slow, slower, slowest, short, shorter, shortest. What this is your word vectors for each word PCA'd down to 2 dimensions. So what these numbers mean nothing. This is just some like projection from like however many dimensions these word vectors were into 2 dimensions. But what we want to get across here is that, you know, you can sort of see that slow, slur to slowest has a very, very similar direction of like meaning as short, shorter to shortest. So what exactly these angles of movement are don't matter, but you sort of see the parallels, right? Like not exactly parallel, but you can see that what these word vectors have achieved is that going from slow, slur to slowest is a very, very similar traversion through all of language as like strong, stronger, strongest, I guess dark, darker, darkest, and all of these other superlatives. So with these word vectors, and you basically have, you know, you've basically taught it that the relationship between slow, slur to slowest is similar to the relationship between all these other superlatives. And this is just one example of like what word embeddings have learned. Questions about this?
This is based on part of a speech or something else?
So not directly. It's not directly based on part of speech. It's really, this more specifically is really just based on all the words that have surrounded all of these words, which could include some part of speech information, right? Like if you think about,
yeah, because all of them are adjective, comparative adjective, and superlative adjective.
Yeah. I mean, yeah, for sure. Just by nature of like, if you think about, all right, what are the kinds of words that would often come after the word like slower or shorter or stronger or louder? Probably like slower than, shorter than, right? And because of this similarity, that has been captured here. And of course, it is typically in way more dimensions than this. It's only because we are like projecting onto just 2 dimensions that it looks like this. But yeah, in doing like word vectorization, the part of speech is somewhat also embedded, because you can imagine you can sort of learn part of speech based on the words around a word. Anything else?
No, thank you.
Awesome. Anyone else have any questions? All right, I have a couple other examples here. After this, we have this example of company to CEO. So another good thing about word embeddings is you're not restricted to words in a dictionary. You can also have it, you will naturally figure out what's the word for like names of stuff? Is it like proper nouns? Yeah, I think it's proper nouns. So it kind of recognizes what proper nouns are. And you can sort of see that the direction from going from like company to CEO is all kind of similar. So one, it recognizes that, you know, these are all entities like companies, and like the difference in the vectors from a company to a CEO of the company is all kind of similar. So it's actually in some way also learning the relationship between like proper nouns. And yeah, these words, a lot of these obviously don't exist in a dictionary, but just because of the way word vectors are trained, you're just looking at unique words and the words that surround it. You're not restricted to dictionary words, which is pretty neat. All right, after this, we're gonna go into the notebook and look at some like concrete code. Any other questions at this moment? All right, let's take a look at this. We're gonna go through so these two libraries, GenSim and Spacey, have two different ways of employing word vectors. So yeah, I've already run this notebook because a few of the cells actually take a long time to run. So I'm gonna talk through those as well. So some of the things that we're going to use today, these are all normal. We have PCA. We're going to use PCA to just like visualize some of the word vectors in a little bit. So for GenSim, I think the easiest way to use and oh, by the way, GenSim uses pre-trained vectors. So GenSim is a library that you can import pre-trained vectors from, and I'll go through those a little bit. Basically, this API allows you to download the word vectors, which is pretty neat. These two I'm not going to use in this notebook, but these two, basically, if you have another file of word vectors, you can upload them and you would use the data path, and this will convert it into the right vector format that you need. So we take a look real quick. These are all the pre-trained vectors that GenSim has. So here, available models. So the one that I'm using here, I believe I'm using Glove Twitter. Let me just double check. Oh, I'm using Glove Wiki GigaWord. So here I'm using Glove Wiki GigaWord. Let me just, oh, here it scrolls this way. You can see here that these are pre-trained word vectors based on 2014 Wikipedia with 5.6 billion words and 400,000 vocab words. So yeah, this will basically show you what the vectors were trained on. And you can see here, it doesn't show the whole thing, but you can see here that Glove Wiki, there's 100, 200, 350. These numbers at the end just tell you how long each vector is. And so depending on how, I guess, granular you want to get with the representation of a word, you can use longer vectors. But today I'm just using you'll see that each word ends up being 100 numbers long. So what you would do here, you can actually just download the vector. So I'll actually download this using the API. If you run this code, you'll see that you're actually going to be downloading the stuff. And then after that, I save all the vectors into word vectors, and you can straight away do a word vector lookup. So just know that there are, in this data set, let me see, 400,000 unique words trained on 5.6 billion tokens. So that means I'm pretty sure there are more than 400K vocab words. You can see other libraries have more, like this one has 1.2 million. So not every word is going to be in this word vector dictionary, but pretty much most words. Like for example, coffee, this is the 100 number representation of the word coffee based on every time the word coffee showed up on Wikipedia in 2014. I don't know, other words, if you look at like caffeine, is that how you spell caffeine? Yeah. This is a representation. Again, these numbers have no meaning as we look at them. You can see that if I type in like a random string of words, you get a key error because that word scramble doesn't exist in the dictionary. So just know that if you have some word that is maybe like less common, it might not come up in the word dictionary. And we'll see in a code that I have later on how we can get around that. It's really just a try and accept. So word vectors have a lot of built-in functions. So one pretty neat thing, you can do like most similar. So here I'm just looking for all the words that are most similar to coffee based on the 100 number word vectors each word has. To be honest, right now I forget what is the similarity metric they use. I wouldn't be surprised if it was like cosine similarity or like Euclidean distance. I'm not sure, but it is a similarity metric that they are using. And you can see here, yeah.
It's cosine.
Yeah, cosine. All right, thanks, Steven. So cosine similarity. So between like coffee, what's most similar would be tea. You can see that there's, I believe cosine similarity is between -1 and 1. So 0.77 similar. And all of these other words are pretty related to the word coffee. Here you can see that I put in the word Hilton. So as you remember, with word vectors, it can be entity names. They do have a good number of entity names. So here you can see with Hilton, you have hotel, Vegas, other hotels. So yeah, pretty neat. There are a lot of methods that you can use with word vectors. One thing that you can do is take a look at the positivity between, look at the similarity between woman and king. And you can also add negative vectors. So you want to find something that's, all right, similar to woman and a king, but not a man. And then they'll give you queen. So it has like kind of really interesting, I guess, mathematical, you can basically do math with words, which is pretty neat. So basically, all right, what is a woman king that also isn't a man? I guess queen.
So Ish, I know that we like can't really understand what the numbers mean in the vectors, but would they be considered kind of like features of the word, or like I know some of the features would be like contextual clues or something like that, but just like a numerical representation of that?
Yes, so we'll see in a little bit that, you know, this vector of, let me just put back like an actual word. This vector of 100 words would mean that our data frame that we feed in to our model is going to be 100 columns. So yeah, each of these is going to be a feature or a column, but yeah, there's no real like meaning behind each column. It could embed like the information of like what the word is, but as humans, we cannot tell where that is. And that is also not the fact. The thing about like an embedding is that that information is embedded in this abstract representation of the word.
Right, but it's just that all of that is a representation for one word, for the word caffeine.
That's right. Yeah, and again, like if you were to use like the GigaWord 300 library, your caffeine would be represented by 300 numbers. So yeah, I mean, yeah, one pretty good thing with using word vectors is you often will have fewer columns rather than if you had like a unique word per column. So yeah, but the downside is if you're finding like your most important features, that won't mean anything. So yeah, other things that you can do with word vectors. And I've also linked to, I think I have it linked, here, to all the different vector methods. So here you can see that I have like analogies where you can see, all right, positive and negative, right? So what is Japan to Japanese? What is that with Australia? You have Australian. And apparently you also have like Zealand, which I'm assuming New Zealand. And Australia to beer, France is to champagne. So pretty neat, the stuff that you can find out through word vectors. And again, this is all based on the information on Wikipedia and what words have been around, you know, the word Japan and Australia. So yeah, a bunch of examples here. You can see here Obama and Clinton, you have Reagan and Nixon, that's pretty neat. And yeah, I feel like this is a fun thing to play around with, but again, let's get into like some of the more important stuff. I guess this one last one. Doesn't match is a pretty cool one. I found this really funny because I guess Brexit happened, but in 2014, I guess they wouldn't have known that. But what doesn't match here? If you give England, France, Germany, and Russia, and of course you're putting this in a list of words, it'll tell you that England is the odd one out, which I think is super neat. All right, so let's get into more like how you would use this in one of your projects. But yeah, before we get to that, any questions?
At this point, it's still sequential. The information is still sequential, right? Because we haven't done a mean word embedding.
By mean word embedding, you mean like different words?
Well,
putting
like
them
with
together?
mean word embedding, don't you lose the sequential information just because you do an average of it?
Yeah. Yes. So that's kind of like, I would say, in using the two different libraries, we'll talk about this next example. I'm actually going to talk about mean word embeddings to basically make like an embedding for like a sentence. But I'm not sure if I have that coded example out, but I'll show you how like these embeddings are going to be different from document embeddings when we do that with Spacey.
On the lab, I put together the headline, and then I put the author, and then I put the short description. And in the lab, it's just supposed to be headline and description. And I was getting really weird results for the king and queen. And so I wonder if like that messed up the sequence of it and was just kind of like throwing it off, especially since I didn't train it very much.
That's likely because the order, by essentially doing this, and we're going to walk through that process in a little bit. By doing that, yeah, you do mess up the sequence exactly of things. So yeah, in this example, I'm going to go through like what a mean embedding is. So very likely when you're doing NLP, your one document will not consist of a single word. So you have to find some way to combine to get like the vector for entire sentence. And so just as like a really quick example, in this sentence, I like my coffee hot. And what I'm doing here is I'm just summing up all of my vectors. Because again, as Stephen alluded to, if I have individual word embeddings, a good way or a fast, simple way to get to a sentence embedding, like some numerical representation of an entire sentence, is to just put all the words together. And so one quick way to do that, and we'll see here, I'm first splitting the sentence and then getting the word vector per each word. And after I do this, I end up with this as like the I like my coffee hot vector. Just to really quick show you all what this will look like without the try and except, you're going to end up with a key error because it's pretty neat. They actually tell you the word I is actually not in the vocabulary. So, I mean, it makes sense because it's a stop word, but that's why we're going to put all of that back. And again, try except, you can, in these except statements, you can tell it what error to look out for and do different things based on different errors. That's more of like a Python thing, but yeah, that is one quick way to get a vector for an entire, like a whole string of words.
So it's just summing them then, like just summing all the different vectors on top of each other?
Yep, that's right. Okay. So if we take a look over here, vectors, vectors is here a list of 4 or 5. Oh, actually we can see here, it's just 4 100 length vectors. And then you're just summing them all together. Yeah, and yeah, it's pretty neat that you can just sum them this way with like the sum, with the Python sum. It just knows automatically to stack all the arrays on top of each other. All right, so just to like round out this part, like vectors, so what? This is some like pre-written code that basically I have all of these word vectors. Let's just see where they are in 2-dimensional space. So you can see here what I'm doing is I'm actually using PCA here, and I am coercing everything down from 100 to 2 dimensions just so we can see roughly where they are in space. So this is just a bunch of really random words. And based on where these words are in space, you can sort of see what ends up being more similar to what. Let's see, this zooming in, I don't know why it's taking a while. So here you can see here, these are countries, Luxembourg and Hungary. and France and Germany are here. These are all European countries. Here we have like food things. We have animals over here. These, I guess, are places. And out of all the places, these are our countries. These are like, I guess, institutions. Like you have universities, school. Australia, I guess, is over here. Assignment, you get, yeah. So yeah, this is just what it looks like in 2 dimensions. You can also do a 3D version of this, but yeah, it's kind of neat to see that within just these 100 numbers, you can sort of see in space what is closer to what. Questions about anything we've talked about so far? All right. Ooh, this is taking longer than I expected. Okay. So the next thing we're going to talk about is Spacey, which is another library that you can use to make word embeddings. So within Spacey, there are a lot of different models. If we just really quickly look through them, you have different languages. You also have within English, for example. Where is English? Within English, you can have different models too. These ones are just, I believe, small, medium, and large. That's what SMMD stand for. And here we're going to use the same data set that we used yesterday and apply some Spacey. So this is already run, so that's good. This is the one that will take a little bit of time. So this NLP variable that I have, loaded the word embeddings onto is really neat. It kind of does an entire pipeline for you. So if we take a look, what I did here, this was our original data set. I basically applied this NLP onto the body of text here and just made it into another column of the data frame. In the data frame, kind of looks like nothing has changed. It looks like it's just made tokens, but it's actually really interesting. So what I did here first is I took the first value here. This entire thing, I just saved it as first Spacey. What's really neat is there's a lot of information embedded as like attributes to this new Spacey object. So here you can see the type of this, it seizes as an entire document, and for Spacey 0 is a token object. So within tokens and documents, you can actually run a lot of different methods on that. You can do the similar things as we did earlier. You can do like similarity, differences. You can print out the vector, which is what I'm going to do as well. So this Spacey library, and I did the small English library, it turns everything into vectors of the length 96. So the first Spacey, this is the entire document, is represented as 96 numbers. First Spacey index 0 is literally the first word. So in this case, it would be noting. So noting has this vector. So what's cool about Spacey is it also embeds, the sequence of words, getting from the individual word vectors to this document vector. I don't have this code here anymore, unfortunately, but if you take all the word vectors and sum them up, they're not going to be the same as the document vector. Just because the document vector that Spacey creates maintains that like sequential nature. You're not doing a mean vector at all. And embedded in that, something that I think could also be helpful for you all, you don't have to use this information explicitly, but you can actually get the part of speech for every single word. So here we had noting that the resonation of, I think this is James Mattis, you have like verb, I forget what conjunction, I don't know what that is, noun, proper noun for James Mattis. You have all the parts of speech, and it's all embedded in this like Spacey object here that seemingly looks like nothing, but there's a lot of information there. Questions about this part so far before we move on? All right. So what you can do is I took the vectors of each, I took each document vector and just turned that into a data frame. I did that with a really quick list comprehension, and NumPy vsite literally just makes the rows, and I have all of this as a data frame. Now that we have this data frame, this is what you would end up throwing into into your classification model or whatever model you want to use. Questions at this point before we move on to the next thing? All right, well, in terms of word vectors, you could argue, yeah, the Spacey's document vectors probably will give you more accurate information on an entire document. Some people find the code a little harder to use for Spacey, so it's really up to you which one you use. These are just different methods of turning your words into numerical representation just so they can be fed into your model. And yeah, this whole class of things where you have individual columns that don't really mean anything, these are under word embeddings, which is, yeah, I feel like one of the newer, hotter things in the NLP world. All right, so the next thing I wanted to share, this is actually not part of the curriculum, but I do think it's very, very interesting. The whole idea of topic modeling, right? So let's say you have a big group of text. Topic modeling will allow you to try and extract what are the main things in this, what are some of the main topics that are going on in this text. Within here, we're actually going to use a model called LDA. LDA stands for Latent Dirichlet Analysis, and it is a model that does soft clustering. So remember when we talked about clustering, the two methods that we talked about, k-means and AJC, those will, each data point will belong into only one cluster. Whereas in topic modeling and in LDA, more specifically, LDA actually gives you like probabilities of a document belonging in a cluster. So we have some really, really quick pre-processing code here. I don't have it. Do I put the link here? All right, I don't have the link here, but I'll send it out later on. There's like a really good walkthrough of the LDA process. But basically, the kind of data that you need is a list of lists, which I know is kind of like, why list of lists when we have like data frames and all that? Basically, data frames take up more memory. But basically, you have a list of lists where each inner list is tokenized text. So here I'm taking the same text that we had from before, that satire, non-satire text. So with this, in this data format, I'm throwing it into this LDA model. This is just the instantiation step. No, not really the instantiation step, but this is like the fit and instantiation step. So again, I feel like the main things that I want to point out here are, this is similar to clustering. You tell the model how many topics you want it to try and detect. And then the rest of these, not as important for now. I'll send out the documentation so you can look at what these hyperparameters are. The main thing here is this one is all of the unique words in your, this is your unique words. No, this is your this is your unique words. And then this is going to be your like term document frequency. Again, I'll send out that walkthrough so you all have like a, it'll explain it a lot better. So within your LDA model, after you've trained it, and this is it fitting onto the data, you can basically print topics. So the LDA model on its own, you can get these topics, and you can see that it exists as a list here, a list of tuples, I believe. You can see like the 0 one is all of this. Oh, I think my computer is lagging out a little bit. Sorry, y'all. But you can see here, there's a tuple that is here that starts with a 0. This is the first topic. This is the second topic, like 1 till here. 2 and onwards is the third topic, and 3 and onwards is the fourth topic. Now from this, you can sort of figure out what the topics are based on the words. So these words that they list here are the most salient words in the topic. So topic 1 is characterized by, all right, say government, official, election. So you can, based on this, similar to when we were doing clustering, you have to manually label the topics. So based on these words that you're seeing, you can sort of create the titles for these topics. So this by itself gives you this output. This part is the really cool thing that I wanted to show you all. There's this library called PyLDA Viz, literally Python LDA Visualization. And it literally visualizes in 2-dimensional space where your topics are, which is really neat. I hope it doesn't lag out too much. Yeah, okay, cool. So it's this really neat HTML output. You can actually save this to an HTML file as well and potentially like embed it on like a web page, I think. But yeah, all you're doing is you're giving it your LDA model. And what this is useful for is for figuring out what your topics are. I think this is way more useful. So for example, you can see here, these are our 4 topics that the model has clustered our topics into. In our first one, as you can see, we have like say, government, official. You can maybe say that this is more like political. Again, let's look at these. This one seems to be more like, I don't know, market, economical. Up to you to decide, again, based on this. And then you have other topics like, all right, this is, I guess, more people, protests, and this one kind of similar. And literally like how far away these bubbles are on this 2-dimensional map are like how similar the topics are. So this is really, really useful as an EDA tool as well. If you're not, if the main purpose of your project is not to cluster, not to cluster, this could be a very, very useful EDA tool that I think is a really cool thing to have in your project. And you can actually get a lot of information here. You can see like relative to the rest of your topic. So this, without highlighting over anything, is the most salient terms in your entire data set. And then here, you can sort of see the overall term frequency versus the term frequency within the selected topic. So I think that's really, really interesting as well. So you can get a lot of information from just this output, which all the information does exist in like different attributes of LDA model. But again, just having this like interactive output, people like. I will say it does slow down your notebook a little bit. So if you want to do this, I do recommend putting this in possibly a separate notebook from like other heavy things. So yeah, this is the thing that I wanted to share with you all that a lot of NLP capstone projects incorporate. A smarter way that I should have gone about doing this is maybe looking at the LDA topics between like my 2 classes, so I can do like a more comparative analysis. So I know this data set talks about satire versus not satire. Maybe I can take a look at the topics just within satire, just within non-satire, and have 2 of these outputs. So yeah. Any questions on this?
What are the numbers at the left side of each tuple, left side of each word on top of this?
On top of, you mean like here?
No, I mean the list of tuples.
Oh,
yeah.
This?
Yeah.
I think
the weight of each word?
I think it is the weight of each word. Honestly, LDA, like the math behind LDA is something that I have myself yet to dive into. So I'm not 100% sure, but I think it makes sense that is the weight of each word.
And because it's using something like k-means clustering, it's important what number we use for the k, for example, number of topics.
Yes, I will say because it is harder to tune this, something that people like to do is based on this output, you can see that maybe 3 clusters makes more sense because these 2 are very close together. But again, let's say within this you think it's too broad, it might be worth increasing the number of clusters. So it's really up to you like to tune this based on what you're going to be using this for.
And again, there is no clear understanding that we are doing this right or not.
Yeah, it's this LDA is an unsupervised algorithm.
Okay, thank you.
You're welcome. Anything else?
For running like an RNN, can you kickstart your RNN by taking the weights from something like the glove library, or is that not possible?
Ooh, that's a good question. Are you thinking of RNN in the context of like predictive text?
Yeah, that, or yeah, pretty much.
Okay, so for those of you who haven't gotten there, RNN stands for recurrent neural network. I always forget if it's recurrent or recursive. But yeah, it stands for recurrent neural network. And it's basically a neural network that is most commonly used in NLP for predicting text. So I have seen some capstone projects where, you know, you can start off by like typing a sentence and it'll like continue the rest of like the story for you. It's actually pretty neat. So within RNN, you basically are going to feed in a lot of examples of like text, just so it knows after what word, what is a good next word. I do think that people have trained RNNs using word embeddings. So I do think that that is a possibility. I myself honestly have not had too much experience with like RNNs with words, but I imagine that that will give you a similar thing. So for example, let's say you have like a very generic word like to, given the context of the word to, if you're using word embeddings, it might be able to make more informed decisions on what word comes next, I imagine. And yeah, you can feed in word embeddings. You can definitely feed in word embeddings into a neural network. I'm just not 100% sure of like how that will change the results versus not. But I imagine it is more information than just giving the words themselves. We'll talk about RNNs next week once we have the foundation of like neural network information. Anything else? All right, I also wanted to talk really quickly about the projects, and if anyone is just having difficulty in like deciding what project to do, I'll just give like a brief rundown of like, I guess maybe my expectations for each project. So let's see, where is the project? Here. So let's just go in order. For this time series project, they do have a suggested question. What are the top 5 best zip codes for us to invest in? This data is basically going to be a lot of like time series data for a lot of different zip codes. So this project, usually what it involves is some way of, you know, training a model for multiple zip codes and then having it forecast on multiple zip codes. And then based on the forecasts, pick which are the best to invest in. You are definitely welcome to tweak this question to something that you find more relevant. What some people have also done is just pick one of the zip codes and then just train a model on that. That is absolutely fine as well. So yeah, with time series modeling, pretty straightforward. Just create this. You're not expected to do anything beyond the linear models that we talked about. You don't even have to include exogenous variables if you do not want to. There is no exogenous data that is provided. So you're welcome to just work with, you know, the theorema aspect of the models that we talked about. And yeah, feel free to like tweak the question to whatever you think makes sense for you. Questions on this?
I have a quick question. Do we have to answer the specific time series model question, or could we source our own data and like ask our own questions as well?
I should have started with that. Yeah, you can source your own data for sure. I will recommend that you don't unless you already have an idea of what data to use, just because my idea is for this project to be a little bit more chill overall before you get into the capstone where you would put a lot more effort in. So yeah, okay. Unless you already have a good idea of what project you want to do, then yeah. And also if you want to do that, just send over the data set so I can, I guess, approve it. Oh, one other thing, I am planning to pair you guys up for this project. If you don't want to be paired up and you want to just work on your own project, the pro of that is you can get started earlier because I won't be giving out the project pairs till probably Thursday next week. Let me know. That is okay. I'm very flexible with this project. Questions about this before I talk about some of the others? All right, so yeah, with time series, there's a lot of flexibility. You don't necessarily have to talk about this question. If you're confused or if you're not sure whether what you want to do is okay, just Slack me and let me know, or we can talk about it at a one-on-one. Next, recommendation system. I will say with recommendation system, we really only talked about the one algorithm, the SVD algorithm, or more specifically, the alternating least squares algorithm, but it is called SVD in the library. So pretty much it's just using that one algorithm, tweaking it a little bit. This project, what will be, I guess, the challenging part rather than just implementing the algorithm will be your interpretation of evaluation, as well as I do challenge people doing this project to do some sort of like function that can help you make predictions. A hint, a lot of that code exists in a lot of the, in some of the recommendation systems labs. But there's really only the one algorithm that you could use here. I mean, there are other algorithms on the surprise library. Feel free to test those if you'd like. But yeah, I'm only expecting, I'm not expecting more than the one algorithm for this project. Questions about this one? I will say the recommendation system project is probably the one that will take the least amount of time just because it's just the one algorithm. But yeah. The next one would be image classification. This is the one that we haven't talked about yet because it's under neural networks. This project, huge caveat, there will be a lot of waiting. So there are pros and cons to having a model that takes a long time to run. What a lot of students that have chosen to do this project end up doing is you just set up the neural network. I'll go through the syntax next week. The setting up of the neural network is pretty straightforward. You'll just set it up, let it run, and while it's running, go back and like read and do the labs and like learn about neural networks. So I think that's if you want just time to like revise your work, maybe you do this project. It is a classification project, so all of the same classification principles that we talked about in phase 3 apply here. So for example, you will actually have the same evaluation metrics. You get to decide whether you care about precision recall, F1, or accuracy. And also, yeah, I don't think there's class imbalance here, so you don't have to worry about smoting an image. But yeah, I know we haven't talked about neural networks, but we will next week. Questions about this before I talk about the NLP project? All right, so the NLP project, also quite similar. It's, I know this one, they don't really give you, well, I guess here they tell you build a model that can rate the sentiment of a tweet based on content. You can tweak this however you like. So based on some of the features that are provided, you can decide to predict sentiment, or maybe you want to classify, I don't know what there is to classify, but you can cluster and then classify, up to you to decide. But yeah, you can also predict sentiment. And I believe with this prediction of sentiment, it ends up being a regression problem. So, oh, I think it is a regression problem, or you can actually make it, oh, sorry, positive, negative, or neither. So it's up to you how you want to feature engineer your target. I don't care if you do binary or ternary, whether you just have positive or negative, or if you decide to not have that middle class, it doesn't matter to me. The thing with an NLP project, NLP is really just the process of going from words to numerical representation of it. So that's the part that you would focus on. Perhaps you test different methods of vectorizing your text. Maybe you use like count vectorizer, TF-IDF, maybe some word embeddings and compare them. But also it is, in the end, you're going to be using classifiers likely. So again, same principles of classification that we talked about last time. And what I just talked about with image classification. Again, you get to choose whether you want to focus on like precision or recall or accuracy. And yeah, the evaluation metrics are all the same. The models that you will use for NLP going to be the same as the models that you use in your last project. Any questions about projects overall? I will be doing the project introduction on Friday of next week. Actually, depending on, maybe I might switch Thursday and Friday, so y'all have one more day to work on it. I'll put out a poll on like which topic you want to work on Wednesday, so that I can like pair you guys up if you want. Again, if you want to work on your own or you want to get started early, let me know. So if there are multiple people starting early on the same thing, I can have you guys paired up sooner. So yeah, just let me know if you want to do that. Any final questions to close out? All right, sounds good. Um,